Okay, welcome to this class on the basics of probability theory. So first of all, this class lecture is about to help you go through chapter 10.1 in this book, which is extremely condensed. This is impossible to read if you haven't had some basic introduction to probability and probability theory. And the same goes for this video lecture. So if you didn't have that, you probably not follow this. But for those who have and are still a bit confused about the concepts they use in probability theory, this class is for you. Because I didn't learn it properly when I was a student, and I was for the longest time very confused. It was hard for me to speak with people in statistics. Which have statistics and probability theory is not the same, but of course, taking statistics probability theory as a foundation. So because I couldn't make sense of what they were telling me, right? So this lecture focuses on what is really a random variable, right? And to me, I mean, you see it. Maybe you've seen this definition that a random variable is any measurable function. That's much, right? But then when you start reading textbooks on probability and statistics, that's not how it shows up. The typical thing you will read is, okay, you have a normal or random variable, normally distributed random variable, we call it x, and then we want to compute, let's say, the variation. So this is an integral. So what I do is I take x, the independent variable, minus the expectation, which here is 0, square, and then against this function here, which tells me the probability density. So the probability of the value x showing up in a certain interval you get by integrating this guy against your measure, right?
Hello. So this is me in my house. Sorry, I forgot to add the square root on the normalizing constant there. It comes later, but anyways, just a heads up. It's it should be a square root over the 2 pi.
So then you would see things like this. So now where's the random variable? Well, it's there, measure x. You know that it seems to be here, right? But I mean, for the longest time, I was under the impression that random variable is just what the statisticians use to call the independent variable. But it seems to be, yeah. Oh, so tough in both calculations, just small x. So here's the big x, here's the small x. What is this really? From your part. So let's start the story from the beginning. So what is the world according to the probabilist? So you have this, you start out with a space omega, which is a measure space. You have omega, you have some sigma algebra alpha, and you have a measure mu. The main difference here is that we don't call it x, we call it omega. And very importantly, the measure of the full space is 1, because these are all possible outcomes of some experiment or whatever you're studying, right? So if you have a point with omega inside, we call that a realization. And so this is the set of all stars. Yeah, this is a specific star. Okay? And then you can have a subset, A, let's say, all yellow cars. Okay, so omega, all cars. A, the yellow one. And this is omega, the specific one. All right. And then what is mu now? What's the probability of a random car being yellow? What is the amount of yellow cars divided with the total amount of cars, right? So the amount of elements in the set, we usually use this symbol. So my measure, since it is finite dimensional, is just counting and dividing with the total number, right? So far, so good. Okay, where's the random variable now? No, talk about things that happen here, events and their probability. Well, the random variable shows up as a function. From here to something which is usually much simpler. So often it's the real line, but not necessarily. It can also be the natural numbers or the real line, the base, something like that. So, okay. So in this example, we can take x can be the amount of mileage, the mileage of a car. Okay. So, as I said, the only condition on random variable, why the hell it's called variable, probably because of this completion, right? But it's a function, and the only condition that we have on it is that it lives on a probability space and that it's measurable. Okay. Okay, so the mileage. And now we can take, for example, the set, let's say 30,000 miles. We're interested in that. So let's do this set. Let's call it I. Now I'm interested in what's the probability the random car I bump into has more than 30,000 miles on the mileage counter there. Well, the answer to that question would then be well, what I need to do is take this axis, send it back to my function x, right? Now I get some set here. Then I need to measure that. Okay. All right, so now the random variable, it showed up as a way to simplify things a bit, yeah? So then it's easier to specify this set over here. So far, so good. I'm all in the story up until this point. But it gets a bit more complicated than that. So they like to work here on this side because things are easier here. So what they will do is they will have a sigma algebra here as well. So what's the sigma algebra on this side? That will be right here. So you have the real line, can be something else, but now in this example, it's real line. And the Borel sigma algebra, always the Borel. Why? Because we want to be able to send open sets back here. If we have any sigma algebra here, it should contain the open sets. There's no need to go to a thicker sigma algebra than that. So the only requirement, is that A should be thick enough that you get all the B images of open sets and all the Borel sets automatically comes along. It will be in here, So, okay, the other Borel sigma, and now we have a measure. So the idea with this measure is that instead of sending things back here, it would be easier if I could just integrate over some sort of probability measure here on the real line. We tell you what the probability of a particular point here, what's the probability that I car has that particular mileage. Yeah. How do we do that? Well, this is something that we actually skimmed over very quickly in the first course. Yeah. So it's actually 2.6. We talk about, I guess they should be called push forward measures or something. But if you have a measure here and a function that's measurable, you can send it over here. So there exists a measure on this place, which you're going to call px, which is mu x minus 1. Now you need to take up your book and recall the definition of what that means. Well, the notation almost explains it, right? So what is this? So px, as Tom said, p is just mu of x minus 1 over p. So that's the measure I'm gonna write here, or work with here. And now things get a bit easier because then I don't really have to bother about this, right? So now if I want to answer this question here, I can just say, well, it's px of my integral I, so that became simpler. And just as a warning for notation, they like to write stuff like this. This is clearly abuse of notation. So the probability, this is with the double line dash, is probability. Always the probability is like given, we don't need to specify it, you know. I mean, but it's understood from the context used to what this is, right? So in this case, this measure. No, but boils down to this guy. But anyway, the probability that x is in this interval, x is we just learned it's a function, it's not a variable. I guess I'm not the first one to be confused here because this, whoever came up with this notation clearly thinks of x as a variable, right? But this is a use of notation, which is fine. We do that all the time. I mean, we call the LQ space the dual of LT, although we know it's not. Yeah, things like this. We take equivalence classes and pretend that they are functions. It's fine. Just you know what this means. It means this. Okay. So then with this, we can now actually understand this formula here, because what is the definition of the variance? If you go to a real textbook, it's when you have to, okay, again, this is a random variable with expectation is 0. So then you have to integrate x squared against your measure mu. Okay, so why would that, if I know that this is a normalized random variable, what does that mean? It means that this guy here, px, is given by this measure, yeah? So then I know my px, but okay, so how can I convert this? Now I have a function here of x, and I want an integral now on the real line, so where x tends into. But again, we look at problem 268 in this book, which basically tells you that when you have such a push forward measure, or what it should be called, what I can do here, instead of applying my function, in this case the square, to this guy x, I can apply it to the independent variable here and integrate against this guy. Yeah, this is what 268 is telling me. So beautiful. Okay, so far, so good. So far, I understand probability theory. My problem starts now then in real life. With some, let's say we have some imaginary statistician friend here who comes along and says, let's take a random variable normalized, yeah, we're going to normalize distribution. Okay, the statistician comes along and he says, well, x is a random variable, a normal distribution. So here in this phrase is telling me many things, yeah? You remember that the left-hand side of probability theory, and then there's the random variable, and there's the right-hand side, which gives you something simple. Okay? So what is telling me, so over here we have this px, and over here we have to measure mu, right? And this is the push forward of mu x. All right. So what is telling me, first of all, is letting me know that px is absolutely continuous with respect to lambda. This means that instead of, so we have a Radon according derivative, and that we're going to call it fx. So this is what in probability theory is called the PDF, or probability density function, right? And it's a natural name because if I have then here now some function here, if I want to know the probability that my value of x pops up between a and b, I need to integrate this function here, fx. So this is a probability density, yeah, because the probability of hitting exactly x, unless your measure here has a singular piece that including has atoms, then the probability of hitting a fixed point is always 0, right? But the probability density exists. All right. So this is implicit in all what he told me, and he even has that this fx is a concrete function, is e to the minus x squared divided by 2. So this is the Gaussian, divided by 2 is to make the standard deviation 1. And then we need a normalizing constant here, which is 1 of the square root of pi. Yes? So he told me all of this. What he didn't tell me is who is this guy? For me, as a mathematician, I don't want to embarrass myself with my ignorance. So I start thinking, to myself, well, maybe. So how can I construct the left-hand side here so that this was all makes sense? Well, the simplest choice is to just do that omega be the real line, because then I can I can take my mu to be the px, yeah, the px and the mu will be the same thing. This is if it's absolutely continuous, otherwise I just have mu to be equal to px. And then what's my random variable? Well, it has to be in this case just the coordinate, well, the most stupid trivial function possible, yeah? Because with this definition, well, what's the probability of landing between A and B? Well, I have to take a pre-image in this function, so I end up on this axis between A and B, and then I have to measure that with this measure. So I get, well, basically mu P of x is really the mu, and that's the one I want. In this case, the normal distribution. All right. Good, so still in control. Now comes the statistician again and says, well, let's take another random variable. I just getting started here. This was x1. Now we have x2 as well. It's independent of x1. Independence I'm going to do in a separate class. Most of you probably have heard about it and won't know what it is. But let me stick with this question of what is really omega here. So for right now, we don't pay attention to this independence. But it says, let me take another one. And, okay, also normal distribution. So I'm like, wait, did you just change omega without telling me now? Because there's no way, so now I chose my random variable here, it's just a function x. There's no way I can squeeze in another one there and make it independent from this guy with the same distribution. So I'm like, the only way I know in my simple world can make sense of this is now I have to let omega be R2. Yes? Well, okay. And then I think a bit, so I want them to be independent. So then I think a bit and I say that, okay, if instead, let me do this is X and the other one is Y. So it's a bit easier with the notation. So in order to make this independent of each other, I need to multiply the probability density functions, right? Okay, and then, yeah, so this becomes the probability density function of my joint thing, right? But then, so if I want to know now the probability density function of 1, so what's the probability that x is between A and B? Well, to get that, I just need to integrate over everything in y in that direction. And you see here, if I integrate out y, the integral is 1, so I get my f of x. Yeah, so this this kind of makes sense. Okay, good. So then, yeah, fine. And now I'm prepared. So the next time the guy comes around and say, well, let's now take C, another independent random variable with Gaussian distribution. I'm prepared. Because I know, this, what we did here was basically, you said Px times Y, the joint measure there, be equal to Px times Py. So the product measure of the two random variables we already had, right? So this is how you create new independent random variables. You create them like this. So if you come to the third one, I say, okay, but this chapter 5, I know it from the book, so I can also do another one here, cross C, and then I just have to change my omega to R3. So, no, now it comes along and he has invented stochastic process. That's it. I say, what is that? He says, well, now I have an infinite sequence of random variables, which are independent from each other. So I go like, wait, with this logic, so now, is this my omega? No, it can get worse, because then it comes back and says, now I have a time continuous random process. And what is that, I ask? Well, it's xt. If t is any number on the real line, so now we're going into r to the power of r. I mean, what does that even mean? Can we depict that? Actually, we can. So if I take the real line, here's my t-axis. So for every t, I have another real axis like this. So I made R2, right? But well, this is a joke. We're not getting R2. We're getting a huge object here, right? Sorry. Maybe I shouldn't have made a joke, but R2, one way to think of it is like at 1, you have one real axis, and at 2, you have another real axis. You can think like this. But here's like for every number t, there's a real axis. So this is something we haven't worked with. Yeah, even, I mean, for Wiener's theorem of product measure, we know how to do that for finitely many. But is there a way to do it for infinitely many products? So now I finally get the guts up to ask the guy, like, okay, so what is actually now your omega? You know what it says? It's not important. What? How is not important? Your whole theory is based on you knowing omega and this mu, right? You need to have it. Well, he says, I know it exists. Okay, you know, yeah, there's this theorem of Kolmogorov. Now, okay, now we get to somewhere. I know Kolmogorov too. Where can I read this theory? Well, you know, usually we don't put it in our books, but I know it exists. Get out. It's useless talking to you. Thank you. I don't need your services any longer. So then, as a mathematician, I go, okay, let me work this. So this Kolmogorov theorem exists somewhere. I don't know why it's. Anyway, I haven't been able to locate it yet. Maybe for sure they have it somewhere, right? But let's go down instead of looking for Kolmogorov's theorem and probably some very general statement. Let's just think ourselves, how can we do product measure on an infinite sequence? So we go back to here, we forget about that guy. We go back to here and see how can we make sense of this. But instead of doing it on the real line, let's make it as simple as possible. So I'm going to go back to the first example you probably ever encountered when you start learning probability, the coin flip. So instead of having, just let's take an infinite sequence, coin flip, and see how we can construct a space omega that reflects that type of experiment. Yeah? So before we do that, let's do finite sequence of coin flips. So first of all, okay, so let's make it so that the coin flip, well, yeah. To make it really easy, the coin flip, it already has one side which is 0 and one side which is 1. Instead of heads and tails, it's 0 or 1. So then with one coin flip, this is my omega. And then my mu, so my random variable is just the trivial one. It gives me 0, 1. So the mu and the px is the same thing. Let me write px. So then px of whatever comes up, either 1 or 0, that has probability 1/2. Yeah, so we are doing discrete, so we're not, well, it's probably with measure, right? It's a measure of the finite set, but we just have to use this number. Okay, so now this is 1. Now if I have n flips, my omega will be this base to the power of n. So now we're talking in sequences. What happens in the nth flip is just well, to take out the nth coordinate of my sequence, right? So x here would be something like 1, 0, 0, 1, 1, 0, up to, well, n in total. Yeah. So the nth one just takes this value, sticks it there, and get the number. So like this, my random variables really correspond to something I can understand, the omega as well. And then what's the probability? Well, if things are independent, you just multiply probabilities, right? Or if you want to take the product measure, because that's how you do the product measure, you multiply. Yes. So our mu here has to be such that if I have a sequence xi, I go from 1 to n. So I take a 1-point set. Okay, so well, the mu is the px measure. This guy we got from when there was just 1. I use the same notation. You do direct product n times, and then on x1 dot 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 xn. And what is it? Does this actually mean? So here we have one of these like rectangular sets. Yeah. So this is px applied to, if we have to that notation. So this coordinate x1 down times dot 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 times, and then px xn, right? So this at the end of the day is 1 over 2 to the power of n, which of course we knew already, but just to make this connected with the theory. So we're basically using product measure here, chapter 5, to create this measure mu. Okay. So now infinitely many coin flips. Now my omega has to be the set of sequences xi, I go from 1 to infinity, where each xi is a member of 0 to 1. Okay. But now I need a measure here. And I want a measure such that, what do I know about this measure? Well, anytime I have a finite sequence of 1s and 0s, I know what's the probability of that showing up. It's this. And since I'm in the discrete world, for that I can compute the probability of any subset of events that happen up here on the chain of n. But of course, I can consider such an event as an event here. It's just that I allow everything to happen beyond the point big N here, right? I guess here should be a big N. So I don't know how to paint this really, but this is the axis. So if I have, let's say just for simplicity, I have a fixed sequence, and then beyond a certain point, I allow both 0 and 1. Here's 1, here's 0, here's 1, here's 0, right? So before a fixed sequence, this is the n number. So the probability of this is that. And then of course, if I have two sequences up to this point, and then allow everything, the probability of that is
twice this and so on. So I know how to compute the probability of any set here, and then you just append this. Such a set, we're going to call it a cylindrical set. By the way, now I'm departing from cone, so to find this construction that I'm going to talk about now, because it exists, so we can do such a mu. But cone doesn't do it. There's a much more slick way of doing it, which I'm getting to soon. So this is you go to Stein-Shakarachi, which is this 4-volume teaching books on mathematics. So basically, it's Stein summing up for the things that he you know. Stein was a famous, I don't know if he did, famous mathematician. Anyway, so these books are very nice to read. Kind of explain things in an understandable manner. So he has this worked out. So now he says, well, any set of this form, I'm going to call it a cylindrical set, right? And then the cylindrical sets, if I take a union of two cylindrical sets, clearly I get a new cylindrical set. Maybe the other set starts here, but that's fine. It's still, if I take the union or the intersection or whatever, it's a cylindrical cylinder beyond some point, right? So the cylindrical sets form an algebra. On that algebra, we have something already, which is this guy here. So this one depends on the dimension, but you know, if you make n bigger, it's the same guy on sequence up to that point if you allow everything else. Yeah, you get it. So I hope. So up, we can use this measure to measure sets like this, as long as they're cylindrical beyond some point n. Okay, so now then, so it's not a measure because we don't have countable additivity, but it's something finite additive. Finitely additive measure is what Corte calls them. Well, Stein-Shakarachi says it's a pre-measure. All right, so now on with that, do you remember how we did the Lebesgue measure? We started with the construction of outer measure, right? So you have some sets, very ugly, E, and you want to give this some sort of size, yeah? So the outer measure we took intervals and we covered this by intervals, and the intervals we know how to measure them, right? What's the length? And then I said, okay, so for any covering of this set E, I can sum up the lengths, and that gives me a number, and then I can take an infimum, that's my outer measure. And based on that, we went on to construct the Lebesgue measure. Now you can do something similar here. So if I take any subset of omega, I can of course cover it with cylindrical sets. And then for the cylindrical sets, I know what is the measure of those. So given any covering of cylindrical sets, I can sum up their measures, pre-measures, and that gives me a number. Now I take an infimum, and I've created something very similar to the Lebesgue outer measure, and in fact, along the same lines. Then Stein-Shakarachi goes on to prove that this is an outer measure. Once it is an outer measure, of course, this is 136 proposition in our book. That says that once you have an outer measure, it comes along with it, that sigma algebra, and on that sigma algebra, the outer measure is actually a measure. So then Stein-Shakarachi goes through the headache of checking that, of course, the cylindrical sets are part of this sigma algebra that we get. The measure we arise like this coincides with these guys that we built it from on the cylindrical sets, and it's also showing that it is unique. So this exists by Stein, Shakarachi, and this is done in book 3. Most of the probability theory is done in book 4, but here we get started a bit. So everything you need for understanding this is in book 3. Okay, so this was good.
Right, and then of course, xn down here would be the same thing. So now we've constructed a space that really connects in my intuition of what is an infinite sequence of coin flips. Of course, we can do it in reality, but in our imagination. And the random variables is something I can relate to. Yeah, it's something just a triviality. Now, Kohn, he has a completely different take on this. Actually, he doesn't discuss the coin flip at all in this concept, but it's implicit in what he's doing. And it's implicit. I mean, you need what I'm going to tell you now. You need to understand this to understand those theories at the end of 10.1. So Kohn says, nah, screw this. This was time checker. Now we go Kohn. He says, well, my omega is going to be 0 to 1, open end. Okay, and then this measure that we really with sweat and tears constructed here, it says, well, you're gonna let that be the Lebesgue measure. And then of course the sigma algebra is the Borel one, but on that interval, so like this, okay? This is not this, it's very different, but actually it's, you can see that it's this one in disguise, because if we take any x and write it in its binary decimal expansion, so since I didn't include 1, the binary expansion starts with a 0, then there's a comma, and then there's a number 0, 1, 0, 0, 0, 1, 1, 1, 0, 1, 1, something like this, yeah, up to infinity. You see what I have here is precisely this, yeah, sequences of zeros and ones that go up to infinity. Now, the coordinate functions I'm interested in here, what are those? Well, they are, so let's say what determines the value of the first coordinate in a binary expansion? Well, so here they are x, so now I have to call them y. So y1, well, this is 0 up until I hit 1/2. Then this guy becomes a 1 and it stays 1, right? y2, the second random variable, I'm interested in what happens in the second experiment. So this one will be 0 up till I reach a quarter. Then it goes up to 1. Then it goes down again when I hit 1/2, because now the 1/2 is 0.01, sorry, 0.1000. Okay, and then it stays 0 until I hit 3/4, because then I get 0.11. Okay, so this is the guy. And now you get the pattern, right? So y3 it's this guy. Now this looks nothing like coin flips, but let's see. So what do we want from these ones? Let's take the probability of y3 being equal to 1. Well, the pre-image of that set is everything what's up here on the shelves, right? What's my measure? It's Lebesgue measure. So what's the Lebesgue measure if I project this onto the real axis, everything up here? It's 1/2, right? Just as this 4 guys make up 1/2. Same here, this is length of this is 1/2 and the length of this is 1/2. So in the end, the probability of yk being equal to either 1 or 0, it's always 1/2. Are they independent? No, I haven't explained to you what is independent, but that's just intuitively. So if I know what's the outcome of the first experiments, I know that y1 is equal to 1. This basically tells me what that, okay, so the question now is, what does this tell me about the value of y2? So I know that I'm here. Well, y2 is 50% down here and 50% up there, so you have still equal probability of being 0 or 1, just as before, right? Same here. Flip it around, if I know the value of y2 is 1, all right? What can I say about y1? Well, it's either here or it's here. Well, 50%, I mean, these two chunks are equally big, right? So where this y1 function is 0, that's half of the interval, whereas 1 is the other half. So this gives me absolutely no information whatsoever. Okay, so now I have an infinite sequence of random variables on a probability space that have nothing to do with throwing a dice or a coin, but behaves precisely like these guys up here. Yeah? We can even go beyond this and say that these two spaces, I wanted to fiddle here, that these two spaces are almost identical. So you have to be a bit careful here. So what can go wrong? So if I take the number 1/2 exactly, yes, then y1 is going to give you 1. Yeah, so these functions, they're continuous from the right? The value here is this, the value here is this, the value here is this. So at this point down here, 1/2, I'm getting 1, and then I'm getting 0, 0 everywhere else, right? So the point x equals to 1/2 corresponds to the expansion 0.1, 0, 0, 0, 0. But there's another one expansion that gives me the same. So if I do 0.01111111 up to infinity, I'm getting the same number, 1/2. Okay, so what am I implicitly using here? How do we convert binary sequences into numbers? So let's do iota from omega tilde, so this is 0 to 1, into omega, which is the binary sequences, more bullshit. No, I want the other way around. So if I have a binary sequence, how do I get my number x? I'm going to call the binary sequence yi. I go from 1 to infinity. And how do we turn that into a number when we do an infinite sum? Yeah, this is what it means, right? So now, if the first one is 1 and then everything else is 0, I'm getting 1/2. Yes? But if the first one is 0 and all of the other ones are included, I'm summing that up, I'm still getting 1/2. Right? It's the same problem as 0.9999999 up to infinity in the usual decimal expansion. It's the same as 1, right? So we have this problem here. The point here is that iota is not injective on sequences with infinitely, well, on sequences that ends with only 1s and ends with only 0s. And this is, well, I mean, it might seem like a harmless thing, but it is a problem because here, if you work in this world, you might easily stumble. We can say something like, okay, let's take a realization such that all the random variables become 1. Well, the problem is that now we're in one of these strings, and that doesn't exist, right? There is a realization which makes all of them except the first one 0, and that's the number 1/2. But the one that makes all of them 1 doesn't exist, yeah? So this is clearly an advantage of this space up here. So if I want these two to become a bijection, I have to deal with these points that become problematic. What are the points that become problematic? Well, I have a finite sequence that up to some point, and then only zero or only one, right? So finite sequence up to some point. This gives me what's called a dyadic number. So something which is of the form. So the problem points are. So of the form L divided by 2 to the power of n, where n is bigger than 1, and L is between 2 to the n and 0. These are the dyadic numbers in the interval we're interested in. Okay, so Stein Chakravarty's way of dealing with this is he's saying, like, look, these points they're countable. So whatever their contribution to the study of infinite sequences of point flips are, I can ignore it. Because the measure of each point is zero, so I'm just throwing away a measure of zero set. He says, well, I'm just going to remove from my analysis all dyadic points, well, on this side of iota, so this is my interval. And on this side, I'm removing all sequences that are either infinitely many ones or infinitely many zeros, only belongs to points. This to me is dissatisfactory because I want to have a possibility that somebody sits and flips the coin and gets infinitely many ones, right? So how can I do that? How can I improve this mapping iota to make it into a bijection? Well, in that case, I have to come up with yet another space that's called omega tilde tilde. Binary sequence. So how am I going to fix this interval? Well, what I can do is I take my interval, and now I'm adding the dyadic points between 1 and 2. And then I let my iota now go from omega again, sequences, into omega tilde tilde. So I have the same expression as before, but I'm going to add the characteristic function of the set. I'm just calling it A, where A is the set of points sequences with infinitely many ones beyond some point. So what does this? So anytime I have a sequence that will give me one of these dyadic numbers, if it ends with only zeros, nothing happens because this guy is not into play. So again, I'm just like this. I'm filling up my interval between 0 and 1. And if I have the corresponding point with only ones, I'm having the characteristic function, so I'm just adding a 1 to it. And then that sends outside. So my omega tilde tilde now is this. And then out here all the dyadic points. Now I do have a bijection between the sequences and these numbers down here. So this bijection, what is the value of it? Or what? So let's think, is it what do we want usually? In mathematics, always when you have some sort of object, we want bijections to preserve the structure, right? What's the interesting structure we're dealing with here? It's the structure we have is sigma algebra, right? So now, if I have an open typical set up here in my sequence space, what are the building blocks of my sigma algebra? Well, what the cylindrical sets, right? So basically, I have a sequence of fixed values, 0, 1, 1, 1, 0, 0, up to some point. And then beyond that point, I allow everything. These serve as building blocks for the sigma algebra we constructed with the approach by Stein-Shakarachi. What does that mean with this mapping here? Well, this one or this one? Well, okay, with this one here. So if I have a cylindrical set, so the first sequence up to, let's say, n of fixed values, it will give me some dyadic points, so some number of this type. And then beyond that point, I allow everything else, yeah? So what I'm doing then is I'm filling up all possible values between this point and the next one, so L plus 1 divided by 2 to the power of n. So you see, when I push forward through this iota, the building blocks of the sigma algebra of the first space, I'm getting small open intervals here, or semi-open, because they're closed here, it's open here. But since the sequence of infinitely many ones is inside, also I'm getting the corresponding point up here before we get to 2, right? So the right-hand limit is not included there, but it's there. So this gets a bit overly technical, but I want to go through this, get my punchline basically. Now, so do we get some funny sigma algebra here? Not really, because now I can take the sequence, I add one more, 1, so I get a shorter interval here. I still have this as the right end point. So I go, instead of n, I have n plus 1 when I start. And I fix my L, so I start here in the middle. That's another one in the image of sigma algebra, omega. And now I can take infinitely many intersections. So when I do that, here I get void because I have an open end point here, and only remains this point. So this point alone is going to be my sigma algebra. Well, then, since I'm allowed to take complements, I can just kick him out, and I'm left with this open set here. Is in the image of my sigma algebra in omega under iota. But once I have dyadic semi-open intervals, I can construct any open interval by taking unions of those, right? So it means that the sigma algebra from here sent through iota will be bigger than the Borel sigma algebra. Yeah, because it contains the building blocks, the Borel sigma algebra. But reversely, the building blocks, the ones we're discussing here, are Borel measurable. So here it's a sigma algebra, which is smaller than the Borel sigma algebra, but at the end of the day, the sigma algebra need to be the same. So, summing up, I have this space here, omega, and this guy. You know, once you have a bijection which completely preserves the structure, we usually call that space isomorphic. Yeah, but here I don't know. But this is the gold standard of mathematics, right? When we get to this isomorphism state, we have two objects. We basically say that well, they are the same. It doesn't matter. You know, like LQ is the dual of LP. We think of it as the same. We don't even bother saying that they are different things. So we have a bit the same situation here. So now I'm starting to think as a mathematician when I reach to this stage of understanding. Maybe it doesn't matter if I work on omega, which has some connection to coin flips, or if I work down here, because at the end of the day, they are the same thing. I just need to know that they exist. Aha! Comes the statistician and says, this is what I've been telling you all along. Like, nobody asked for your opinion, okay? Shut up. Off you go. But right, he has a point. So where would I like to work as a mathematician if I were to study the sequence of coin flips? Up here, this space, or one of these two down there, so just an interval on the real line. But clearly, the interval on the real line has its benefits. In the Lebesgue measure, well, first of all, the Lebesgue measure, I understand. This measure we constructed here, I don't know what that is. This is to me a completely new object. I have to do some algebraic manipulations of my random variables. Well, here the random variables are kind of intuitively easy, but how do I work with them? Whereas these are functions I understand, yeah? So I would probably opt for working down here. Okay, so we're here. I have y1 is equal to this guy. Y2 is equal to this guy. Y3 is equal to this guy, and so on. 1, 2, 3, yeah. Too long. But okay, and now similar to what we did before, but not really, because now we don't have the dyadic sequence. I'm going to do the same sum. We're going to look at the sum I goes from 1 to infinity, and now these functions divided by 2i. This is like, I have here a point x, so I'm doing, this will give me the binary expansion of that, and this will give me back the numbers. I'm just giving back x. Okay, so that would be so fascinating. But what is then now really nice is that he says in 10.1.30, he says that, well, it doesn't matter if it's precisely these guys, or just, I can take any sequence of random variables with a Bernoulli distribution with 1/2 to set that half the time equal to 1 and half the time equal to 0. This is just one choice. If I do this sum for any such sequence of random variables, I'm getting uniformly distributed random variable. Okay, so meaning, so I'm getting some function here, such that if I take the interval from A to B here, this is my x, and then I do the pre-image of this, I'm getting some shit down here. But uniformly distributed means that the pre-image of the interval A to B, Lebesgue measure of that, because remember Lebesgue measure is my mu, is still equal to B minus A. Okay? So it's very hard not to explain talk to video and think, how could I make even two functions which are independent from each other and have this property? Yeah, of course the function, this one, has it, but once I have him, it's impossible to choose another one which is independent from me. Yeah, that's just out of the question. So here in this 10.1.30, it says that, well, one way to do that is look at such sums, but I just use different yi for one guy and for the other. So we can go back here, and then I go like, okay, let's pick all the odd ones. So this one plus this one plus the fifth one, and then I take the second, the fourth, and the sixth, and so on, and I add it up with these weights. Now I'm going to get two functions that are independent and both have this property. Okay, so how would such a thing actually look like? I started thinking about it. Could I come up with some expression? Maybe it's like some sawtooth thing. Now, after some thinking, I gave up and I went for MATLAB and implemented it. So let me see if I can share screen. No, idiot! I don't want this. No, I want this. Jesus Christ, I hate computers. This is so shit coming on the food tool. Every time it's coming on the food, I have to do stuff. Boring the way. Okay, fine. All right, here we are. And now it's a bit bigger. Okay, here you see. So this is an incarnation of two functions, two random variables, each independent of the other. Which are uniformly distributed. Okay. Here. So now if I can make two, I can easily make a lot. Yeah, because here I have a countable bunch of them, Yeah, so for every number, 1, 2, 3, 4, 5, 6, so on. I have one function like that. Now let's take a grid. So here I have n, here I have n. So 1, 2, 3, down, 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 down. Now I can enumerate these, yeah, for example, like this, more popular one easy way. I can put at each point here one of these guys, yeah, and same here. And now I can get one variable x1 by just summing all of them up according to that formula. X2 by summing all of these up according to that formula. X3 summing all of these up. And this 1017 tells me that they're all independent. Now I have an infinite sequence. Yes? So basically what I create is an infinite sequence of random variables independent and they're all uniformly distributed on the space. Here's our omega. Here's the sigma algebra. And here's my vector. Now, isn't that beautiful? To me, it's mind-blowing that something so small can contain in it something so big. Because remember, when I first talked about how to construct this, I needed to do basically this. Yeah? But no, you don't need to do this. Just this. Fantastic. Okay. What about other random variables? So now, let me say I want random variables on the real line. Instead of 0 and 1, I want them on the real line with a specific probability measure here. So your px, if you want. Yeah, you specify that. So you want some x random variable with px equal to some fixed measure gamma that you say. And then now you want an infinite sequence of random variables with this particular measure. Then there is the effect. Okay. Another way of phrasing the same, because they like to talk a lot about distribution function in probability theory. What's your distribution function in this setting? It's the probability that, so your fx, your distribution function, is the probability, well, in this case, gamma is not new, but something is between minus infinity and your x. Well, this we know. This is just the functions that we studied in chapter 4, right? Anytime we have a measure, we have such a function. Okay, so then I think this. We have something that starts at 0, goes slowly up, and here it goes, and it goes at sharp jump, right? And then, okay, but it doesn't go above 1. Okay, it will have jump if and only if the measure has some singular point. It's easier. So now, when the theory goes ahead, if I don't have jumps like this, so if the measure doesn't have atoms, it's called. So it needs to have a singular piece, but also the singular piece needs to have some atoms. If it doesn't have atoms, we don't have these jumps, and I get something that continuously increases, that's invertible. So let's just think that we're in the invertible case first to understand 10, 1, 15, or something 16. So the funny thing is, once you have created a uniformly distributed random variable, it's very easy to create this random variable. Yeah? So let y be a random variable. Something that randomly takes points here uniformly with uniform probability. Okay? Now you want the random variable x such with a probability of landing between A and B, so you want the probability of X being in the interval A to B. So remember, I don't need to specify if this is closed or not if I don't have atoms in my measure. So we just do that. Okay. The probability is I want this to be f of B minus f of A. Now, if I use here's f of A, here's my f of B. So if I use some random variable which is uniformly distributed, the probability that he takes a number in this interval is f of B minus f of A. Now, if I take that point and I send it through the inverse here, I'm getting a point down here, right? So, point here, if y is uniformly distributed on 0 to 1, then f minus 1, y, let's call this x, has distribution function f, or in other words, has this measure gamma as its probability measure on the real. And this actually works. I mean, I've used this in some paper I was writing about modeling coronavirus and yada yada. So if you want to have some specific distribution, just make a uniform distribution, and you need to let MATLAB randomly generate numbers between 0 and 1, and then you send them through this. And now you have created the random variable with this distribution function. Very simple, so this is a practical tool. But of course, here, it allows us to blow this example up. So what we did here is we created an infinite sequence of independent, uniformly distributed random variables. Now let's just throw in this guy on them. And we created an infinite sequence of independent, this guy is not going to mess with independent random variables with a fixed distribution function. And the measure space that incorporates all this is still this one. Very, to me, mind-blowing. I don't know what your take on it, but okay. So this was the end of this lecture. That's Corollary 10.160, and now I completely adopted to be a statistician. He was right. So now that with this understanding, as long as I know that he exists and these guys exist, I don't want to know too much. I don't need to know the details. You remember in the first board I had, I raised it now. So the left-hand side, it's complicated to work on the left-hand side, but as long as you know it exists, you can work on the right-hand side. Well, things are much easier. You can complete things, yeah. I thought I was done, but then I sat down and looked at it and realized I wasn't. So first of all, I just want to say, of course, I can have different functions here, and now I created an infinite sequence of random variables with basically any distribution function, yeah, independent, but not. And it doesn't need to be even on the real line. But okay, so that was one comment. Yeah, maybe just to illustrate a bit what I mean when I say that the world is simpler on the right-hand side. So let's take a very concrete example. There's this law of total expectation. So I hope you know what the expectation is. I'm not going to explain it. So it says that the expectation of x1 is equal to the expectation of x1 given knowledge of x2. To me, this is complete. It was very hard for me to still is actually I get confused. What the hell do they mean by this? I mean, I know there are some integrals behind, But if I can just see the integrals, it's usually something simple, but when they write it like this, I go, okay, anyways, it's a different mindset, that's fine. Okay, so I said we have the left-hand side of probability theories over here. And then we have two random variables here, x1 and x2, and that means that my right-hand side here needs to be the plane, right? This is the right-hand side. This is the left-hand side. So to begin to prove something like this down here, I wouldn't know where to start. But over here, okay, so what do we have? Now let's take a small square here. We want to measure that, we send it back here. So basically the measure we're working on here in the two variables is x1 cross x2, e that, so it's mu, and then x1 cross x2 inverse function. Yeah, so this is the push forward measure of this into here. Okay, but then, of course, I also have the px1, yeah, which will push forward if I just take one of them. And what is that? So the probability of having a set E here is, of course, the probability of this bigger measure of having E in the first coordinate and anything else in the second coordinate, right? So like this, we see, okay, so now assume, sorry for poor disposition of the blackboard, but now assume, this makes things much simpler, that this is absolutely continuous with the two-dimensional Lebesgue measure. So basically then, here, if I add the set, well, not E because I have E there, but A, this is just integrating A, and then I have this probability density function. Yeah, so this is my guy. And then down here, so what does this mean now? I'm integrating E times R, this guy fx1 cross x2, the lambda, well, right? So this basically, say, of course, this is also then equal to integrating over E, just this probability density function of x1 alone. So this is a function of two variables, here's a function of one variable, the lambda 1. So by this, we deduce that fx1 of x is equal to integral fx1 cross x2 xy, and just let me just write dy, yeah, over r, and vice versa. We can get fx2 as well, right? Okay. Now there's this idea of conditional random variables, I think they call it, or something like that. If I know the value, which way do I want to do this? If I know the value of, yeah, okay, so if I know the value of x2 or y, okay, are mixed up x1 and x2 and x and y. Here's y, there's x, right? And it's x, very a bit simple, separate like that. So if I know the value of y, now here's a probability density function. Of course, the probability now that y is fixed is going to be given by the probability density function on this thin line. But then I want the integral of that, of course, to be 1. So put it like this, okay? This is, notation can vary a bit. Okay, so x given that y is equal to some fixed value y, and then this is a function in little y, so now I can take that over here, right? So then if we have in this setting with absolute continuous guys, we see that the probability density function of x given that y equals to y is a function in x, which we get by taking the joint one and dividing with the integral, well, by dividing with the integral x comma y dx, but then we decided also that this was f of y, right? Okay, so now if I want to prove this formula on the right-hand side, let's see how we can do that. It's also very easy. Okay, so let's look at it. Okay, what is this? This is integral of the variable x against my measure, well, ex1, so fx x dx if you want. But now I want to involve this. This is an integral over r. But now I want y pulled in into the game. This is still the integral now. I'm taking this guy. Well, technically I do the y first and then the x. Yeah. So when I integrate out the y variable, I'm getting in, right? We agreed on that. And now you see, now I want to use Fubini's theorem, so I can swap the order here. And then I'm gonna divide and multiply with this guy. And then I do Fubini, as I said, so x comes first. I can put my dx there and then my dy here. And then that's double integral at this point, both are double integral. Okay, but this is the probability density function of x given that y equals y. And now I'm integrating x. So what is this? So what I'm integrating now is the expectation of x given that y is equal to y, f of y, y, dy. And in probability theory, if you just integrate a function, in this case, this guy, which is a function of y, that is actually the expectation of that function. So here, against the probability measure, which for the variable y is this one, yeah? So here we have the expectation of this function, which is the expectation of x given y equals y. So here's just one example of what I mean when I say that it's easier to live here than here. So as long as you know that this guy exists, we can just go here and start working. Yeah? Okay, now for sure I'm going home. It's over 9. Thank you very much for watching. See you next video.